Hello, welcome back. In this section we shall see how to build a Gpio library from scratch, and we're going to start from the very basic building block. We're going to go to the reference manual and the datasheet and get the memory address range of where our Gpio port is, and then we come to our Cal UVision and then assign symbolic names to these addresses. And once that is done, we create a driver that would enable us to interface with the hardware. And once the driver is done, we build a library on top of the driver. All of this we're going to do it applying object-oriented principles. Once we've done this in C language, we're going to go on either in this section or the next section and start the same process but in C++. And the reason why we start in C language is for you to start getting the tiny nuances between C and C++. The difference is not great. It's not a large difference at all. It's just a little difference. So if you write it in C language and you see how the C is transformed into C++, it is easier to understand than to simply start writing in C++. So I hope you sort of find this process useful. So let's get started. So I'm going to create a new project by coming over here, project, new UVision project. I'm going to store it in this folder I've created. I'll call this Gpio, or simply call it Gpio. Sorry about that. I'll say Gpio like this. Okay, and my board is the Stm32f411 VET, and I'll select this, click OK. And the CMSIS, I'll select the core, and the device, I'll select the startup, and then OK. Right, so my target is the Stm32f4 board. Source group here, I'm going to rename to App. I'm going to right click over here, add new item. I'll select C language, .c file, and I'll give it the name main. Right, so there's our project. Okay, so we're going to write Gpio driver from scratch without using CMSIS. Remember the LED project, when we wrote it, we did this. Right click, include Stm32 blah blah blah.h. This over here gave us access to the drivers written by the collaboration of Stm32 and ARM using CMSIS. But we're not going to make use of this. We're going to write our own from scratch so that you understand how the principles of reusability and inheritance are used in order to write these driver files for us. So okay, before we start, I've got to give a bit of intro on how microcontroller ports work. Actually, I'm going to attach a theoretical lesson to this. I'm going to attach a theoretical lesson to this section. Perhaps you may have watched the theoretical lesson already, since I'll put that on top of this practical lesson. So just bear with me. That lesson is taken from one of my other courses talking about the same thing, and it's basically talking about how Gpio ports and pins are structured. So in modern day microcontrollers, we can classify Gpio pins we can classify IO pins, I should say. IO stands for input output. We can classify IO pins into two categories. We've got GPIO and we've got SPIO. GPIO stands for general purpose input output, and SPIO stands for special purpose input output. So GPIO is basically for normal input output, hence the name general purpose. SP is for special functions, and special functions here refer to functions such as ADC, UART, SPI, I2C, PWM, etc., even USB. So in order to use our GPIO, we can keep it. In order to use our I/O pins, whether it's PA1, PA5, PA3, etc., we can keep them configured in their general purpose mode, or we can configure them into their special purpose mode to serve as a pin for a special function such as UART or USB. Right, so in our LED example, we configured our pin to be in its general purpose mode. It was an output pin because we needed to create an output, set write 1 to output 1 from the pin, and by outputting 1 from the pin, we get our LED to turn on. Right, so that is the short overview of GPIO pins and GPIO ports. So in order to use any module, peripheral, or any part of the microcontroller, we've got to enable clock access to that part of the microcontroller, and this is due to something known as the clock gating mechanism. It helps the microcontroller save power such that clock is open or clock is only enabled at the parts of the microcontroller that you are going to use, rather than have the entire microcontroller with clock enabled. That consumes much more power compared to just, you know, enabling the bit that you want to sort of use. So we've got to enable clock to our peripheral, which is going to be a GPIO, and we have GPIO port A, port B, port C, port D, E, and H. So we've got to decide which one we are using. So we've got to enable clock access to it, and then once we've enabled clock access, we go ahead to configure it, whether it's input or output, etc. But because we're writing a driver, we're going to make it in such a way that the user can simply decide which GPIO they want to use, rather than we say we're using just GPIO A. It's going to be completely reusable, such that you pass a simple argument for GPIO A, or if you want GPIO B, you pass the argument GPIO B and you get to use it. So in order to get the addresses that we require, we need to take a look at how the microcontroller is laid out, its block diagram, as well as its memory map, to see the memory ranges of the GPIO, since we're dealing with that over here. So if you are using CalU Vision, you can come to the Books tab over here. If you are not, then if you're using a different IDE, you may have to search these documents from the internet. So the first document we're going to take a look at is the Stm32f411 Datasheet. I'll double click this and it's going to open like this, and I'm just going to scroll down to the block diagram. There's a block diagram somewhere. Okay, it's over here. So that's the block diagram. This block diagram gives us a layout of our microcontroller. Right, and okay, this is what it looks like. So in ARM architecture, there are two types of buses generally. We have the APB bus, as you can see over here, APB. This stands for Advanced Peripheral Bus. This is the old bus that ARM has been using for a while. This is the legacy bus, they would say. And we also have the AHP bus. And we have APB1, APB2, AHP1, AHP2. So we have the AHP bus, and this stands for Advanced High Performance Bus. And this is the newer bus. Right. The difference between the two is that the AHP allows faster access to the peripherals connected to it. As you can see over here, it's written AHP1 100 megahertz, and APB, as you can see, it says 50 megahertz max. So wherever you see AHP and APB, you can access the same peripheral. Sometimes, based on the layout, there are peripherals that you can access the same peripheral either with AHP or APB. So you use the AHB if you want to access it faster. So that's the difference. And these buses allow us to enable clock access to the various peripherals. So as you can see, this is AHB, this color, and you can see our GPIO ports, all of them connects to AHB. You can see GPIO A is connected, GPIO B, C, D, E, and H. So we're going to enable the AHB. We're going to go through the AHB in order to be able to enable clock access to these ports. These are the ports we're working with. And because they are connected to AHB, AHB is their bus. We've got to go through their bus in order to be able to enable clock access to them. It's the AHB one. So we would have to find its address so that we can write something to that address that would enable clock access to these. Right. So this is it. So if we are dealing with other peripherals such as UART, over here UART is the same as USAT. It's written USAT here because the full name is Universal Synchronous Asynchronous Receiver Transmitter. So if you don't see the S and it's just UART, it's because we often use just the asynchronous bit of it. That is why you hear people saying UART rather than USAT, because we rarely enable the synchronous part of it. It's often initialized for asynchronous communication. Okay, so once that is done, we need to see the memory map. I'm gonna come over here and search page 54. Okay, so this over here is the table, and it says the register boundaries. This is the memory map of it, but the simplified version is this. So what we would want to find out is the we would need a number of base addresses. Rather than fetch the complete address, we would get a base address and then sort of use offsets. We would just add a bit of offset to that base address to get to the next component that we require. If this is not very clear, no problem. When we start implementing it, you would see. What I'm going to do is I'm going to get the peripheral's base address. Right. We started over here. We can see that this is like the highest address. So I'm going to go to where the address starts. As you can see, when we go down, the address, the starting point reduces. Now we are at 0x4002. When I scroll down, I expect to, okay, now we are 0x001. Okay, 0x400. Let's see. Okay, so that's the starting point. This is the this is going to be what we will call the peripheral base. So this is the base address for all peripherals because they start here and then it ends at the top there. So I'm gonna get this base address here. I'll copy this and then I'll come to our main.c file and I'll say define. I'll create a symbolic name for it using define. Define. I'll say perif base. Right, and I'll add a U here to just show its unsigned number. Right. Okay. So now we have peripheral base. I'm going to get another address, the AHB1 peripheral base. So I'm going to get AHB1. Remember our GPIO is connected to AHB1. Okay, over here we have APB2. So let's see. This is AHB1. So as you can see, AHB1 starts from here, right? Meaning if we just add, if we add only this bit 20000 to our peripheral base, it will take us to AHB1. So what I'm gonna do is I'm going to copy this. Remember, if I subtract this, okay, maybe I should copy the whole thing and show you. I've copied the whole thing. I'll bring it over here. paste it here as a comment. I'm going to create a new symbolic name here. I'll say define AHP1 peripheral base. And this is going to be base address, peripheral base, the peripheral base plus and then plus is going to we're going to say plus, this is what we copied here. I'll put this over here, but I'm going to replace this 4 with 0, because if we add this to this, we get this over here, right? So we've got our AHP peripheral base as well. Okay, moving on. Next, we're going to find something known as RCC base. So RCC, let's see, and that is going to be an offset from peripheral base. It's because AHP is part of this group peripheral, and then RCC is a subset of AHP. I'm designing it this way so that when you see the CM6 library and the CM6 drivers, you'd see that it matches the same format that we are using. When you take a look at the STM32 drivers and hardware abstraction layer HAL, the HAL library, you'd see that it follows exactly the same pattern that I'm using over here. So we're going to find RCC base. RCC stands for something, I suppose, reset clock control. Yeah, I think it's something like reset clock control, and that is, yeah, that is the one that gives us access to the clock control. But it's part of the AHP group, since you know our since the buses we are dealing with is connected to the AHP1. Since the peripherals we are dealing with is connected to the AHP1 bus. So anyway, without talking much, I'll find RCC. Let's see. Where is RCC? Okay, this is RCC. Okay, so RCC says this its start address, but we know we just have to subtract the 0x4000 because that is our peripheral base. So what we have to do is get 0x00003800 plus or okay, without talking much, I'll just copy this again. I think that should be my new method. Okay, so I've copied the RCC starting point. Right, I'm gonna come over here, create a new symbolic name. I'll say define. I'll call this RCC base. And what I'm gonna do is I'm going to say AHP1 peripheral base plus, and then plus over here I'm simply going to say 0x300, and then I'll put a U here. I should have put a U here. Remember, this over here, this number over here is the same as cleaning all the preceding zeros. It's implied, right? So I could put zeros here or just keep it like this, right? So anyway, why did I do plus AHP perif? Because if we take AHP1 peripheral, remember AHP1 peripheral base is this number here plus this here. If we take this plus this and then plus this, we get this. You see? So I can simply say AHP1 peripheral base plus this, because AHP1 peripheral base is this plus this. Very, very simple. Right. So we've got that. Let's let's see, do we need further addresses? Yeah. Okay, so let's get GPIO A base. Let's get GPIO A. Let's get the various GPIOs. Since we're not just dealing with LED, we're designing complete, driver for all the GPIOs. So I'm going to go back to my reference or my data sheet. GPIO A base. GPIO A base starts from here. So we need to fetch that. So I'm going to copy this. And then I'm going to put it over here. And I'm going to come here and see. Define GPIO A underscore base. And this is an interesting one. Why is it interesting? It's the same as the AHP1 peripheral base. So I can simply copy this and put this here, and it's fine. Because see, this is GPIO A base that we copied. It's this plus this. I can, to make it uniform, I can just let you know it's plus 00 U or something. But it's the same as this. Okay, just for a good look, I'll keep this here. Okay. So we have GPIO A base. Okay. We can let's see, we can include GPIO B base. GPIO B, C, D. Okay, let's include these later. Let's just go ahead and make sure this turns on our LED just to show you how it works, and then we come and we build upon it. Okay, so now we've got this. Interesting. We've got our registers. Now we're going to take a look at a different document. The first document we were reading is the data sheet. This time we need to find the register information, and we find that in the reference manual. So I'm going to double click here to open this document here. Right. So what we're going to do is we're going to take all the registers that relate to GPIO and keep all of them in a structure data type, and we're going to arrange them precisely such that they are offset from the GPIO base address so that we can access them in a particular way, and I'll show you what I mean. So let's go to the part of the reference manual that talks about GPIO. We can start from the table of content. Let's see. Okay, should be up here somewhere. Interesting. Okay, that's GPIO. Page 144 it says. Right, over here it talks about GPIO features and then GPIO registers. Okay. We're going to use the same order displayed here to create the members of our GPIO structure. As you can see over here, it says GPIO registers, and we've got GPIO X underscore mode R register, and then we've got the OTYPER register, OSPEEDR register, etc. We're going to follow. The first member of our structure is going to be mode R, the second member is going to be OTYPER, the third member is going to be this, and that. We can read a bit about the GPIO registers by clicking over here. And it says this section gives a detailed overview of the GPIO registers. GPIO port mode register. As you can see, the offset is 0x00. This means this is the offset of this register from our GPIO base address. So that is why I'm going to make this the number 1 member of the structure. After this register, we have another register. It's the GPIO X OTYPER register. This is known as the port output type register, and this one's offset is 0x04. As you can see, when we go down the list, the offset increases. So the offset after this register is going to be greater than this, just like the offset of this one is greater than this first one. So when I come down here, the next register, as you can see, the offset is 0x0c. This is the PUPDR register, pull up, pull down register it is called. And when we go further down, the next register still has a greater offset compared to the last one. This is the one after the pull up, pull down register. After that, we have this. Right, so I'm going to arrange them like this. So let's go to our CalUvision. I'm going to declare the members, which are our registers. I'm going to declare them as volatile type. So I'm going to use a define statement over here. I'll say define, and I'll say __ IO, and then volatile. So whenever I use this __ IO, the meaning is volatile. It's like declaring a volatile variable. And once that is done, I'm gonna come over here. I'll create a structure. I'll say type def struct, open, close, and then I'm gonna call this structure Gpio _ type def, like this. Right. So let's go back to our list. The first register was the mode register. The mode register, its offset is 0x00. Okay. So I'm gonna come down here, and in here, the first member of the structure is volatile. So I do __ IO, uint32 _t, and the name of the register, we can call it capital modar. The reason we get in this is because we have to include stdint.h. Like this. Okay, so this is the first register. The next one after mode register is the output type register. So I'm gonna do __ IO uint32 _t output type register. That's what it's called. The one after that is the output speed register, as we saw earlier. Let's see. Indeed, it's the output speed register. So if I access this, this will correspond to the offset. Why would this correspond to the offset? I'll leave that for you to guess. Can you guess why this would work? Okay, so just like an array like a structure, right? An array compared to a structure, they have one similarity in that the address of the structure is the same as the address of the first member of the structure. In an array, the address of the array is the same as the address of the first element of the array. The address of the array is the same as address of the array index 0. The address of the structure is the same as the address of the structure member 1. Right. So we get this. So if we just come to structure member 1, it's the same as the address of the structure, and the address of the structure is going to be the address of our GPIO port. Right. So GPIO port is the address of the structure. If we go offset 00, it's still the address of the structure, and we can verify this. Why do I say we can verify this? Well, mode register offset is 00, meaning the offset to get a mode register is the same address as the GPIO port register. It's the same address as GPIO X. It's the same address as the GPIO port. The port is not a register. The port is you can think of the port as a set. GPIO A is a set. It's a base address, and from this set we have different registers that belong to it. So the address of mode register is the same as the address of the particular GPIO port. Hence 0x00 in the same way, because the our structure is equivalent to the equivalent to our port. The first member has the same address as the structure, hence offset 0x00 works. Now the question is, it says the next one has offset 0x04. Why do I think just putting this here would correspond to offset 0x04? Why do I think this will correspond to? I think you cannot see. So the next member in our structure, member number 2, we say is output type register, and its offset according to the reference manual is 0x04. Why do I think just by putting this here we'll go to the port base address plus 0x04? Why do I think that would take us to the port base address plus 0x04? Well, this is in the data type. If we use a different data type here, all of this will break down. Uint32_T is a 32-bit data type, hence 4 byte. Right, so this gives us 4 byte. This is the next 4 byte. After that, if we declare another uint32, it's going to be another 4 byte. And if you take a look at the registers, this is the offset of output type register. You see, if we go, the next one is +4. If we continue, this is +4. C is 12, A is 10, B is 11, C is 12 in hexadecimal code. So if we go, it's +4 +4 +4. It's because our data type here, uint32_T, is going to ensure this +4. 32-bit equals 4 byte. Right, if you don't understand any of this, just send me a message. I'll be delighted to elaborate. So we go to the next one. The next one is the OS, the output speed register, or do __IO. And then uint32_T OS PEEDR. Yeah. And the next one after this is the pull up register. Yeah. The next one is the pull up pull down register. So I'll do __IO uint32_T PU PDR. And then the next one is the input data register. I'll do __IO uint32_T IDR, like this. The next one after this is the output data register, __IO uint32_T ODR. And I know this because I've written this a number of times. I don't need to always come back and show you, but you can check. You see, we did IDR and ODR. So yeah, the next one after ODR is the BSRR. This is known as the bit set reset register, and we can use this to set and reset our pins. It's like a shortcut. So I'll do IO uint32_T BSRR. The next one after this is the lock register. I'll do __IO. We can use this to lock our pins. uint32_T, and this is spelled LCKR. And the next one after this is an interesting one. It is known as the alternate function register. Okay, so we have GPIO alternate function low register. We have two of these. We have AFRL for alternate function low, and AFRH for alternate function high. You see this other one H, and this is the other one L. So rather than have H and L, I'm going to just create AFR, and I'm going to create an array of size 2 to hold them, and this is going to perfectly correspond with their base address, such that L would always be the first element in the array, and then H will be the second element in the array. Right, without talking much, I'm going to declare this as __IO uint32_t AFR alternate function register, and then I'm going to give a size of 2 like this. Okay, right, so this over here represent the list of registers we have that belong to our GPIO port, regardless of the port you are working with, whether it's GPIO port A, port B, port C, port D, E, or H. These are the registers, the set of registers that the port requires. Next, we would have to create a structure for our RCC. Remember, it is through the RCC that we can enable our AHP or APB, depending on the peripheral we are using. We've got to go to the part of the reference manual that talks about RCC and create a similar structure for its registers. But we will do that in the next lesson. So I'll see you in the next lesson.